via ergodicity of the tensor product in Riesz space. Such a long title. So thank you. You can use it.
Oh, no, it's fine, thanks.
What? Oh, okay.
Thanks. Yeah, how do I use this? Okay, press. Okay, just like that. And is there a pointer? Yeah, okay. All right, hello. So that's the name, and it's been said already. And so this is joint work. It's with Wenchi, Bruce, and Amin, and that went missing, but I'll fix that later. So, so what we're going to do here is we want to see what's our purpose. What are we going to do with all of this stuff? And once we've done that, we're going to look at the preliminaries for the Riesz space stuff, and then get to the result that we want, which we'll see in the purpose. So in the purpose of this, if we take a classical, the classical setting with measure preserving dynamics, we start with our non-empty set X and put a sigma algebra on it. Let's call it calligraphic B. And we'll have a probability measure on this sigma algebra. And then we need to introduce a measure preserving transformation. So this one I will use tau to denote this measure preserving transformation. So it is a mapping or a function of X into X, which satisfies the property that the measure of the pre-image of the set A under tau is equal to the measure of A whenever A lives in the sigma algebra. And so all of that together, we'll use this ordered quadruple XB mu tau to denote it and call it a measure preserving system. And just say MPS. Where are you? Somewhere here. An MPS, because it's easier to say. So when we take an MPS, XB mu tau, there's a result which characterizes ergodicity, and it asserts that it is slightly different to that is to give weak mixing of our measure preserving system. And so our system is weakly mixing if and only if, out the way, that condition holds there. So what we want to do, thanks, we want to build a Riesz space analog of a measure preserving system. And then we want to have ergodicity and weak mixing defined. And once we've done that, we then want to see how to characterize weak mixing using the tensor product. And the reason why we want the tensor product for this is in the classical setting, there is a result which uses the product of different probability spaces and different measure preserving systems. So it takes the Cartesian product of the sets and then the tensor product of the sigma algebras and uses a product measure. So that's our setup, and we want this result. So now we're going to start with defining a conditional expectation operator, and we're going to use this little theorem to slightly change the definition to make life easier. So the definition, as we've seen, or just now, but we say that T is a conditional expectation operator on our Riesz space E whenever E is a Riesz space with weak order unit and T is a positive order continuous projection on E, and which has the property that its range space is a Dedekind complete Riesz subspace of E and it maps weak order units to weak order units. So TW is a weak order unit whenever W is a weak order unit. And it's quite helpful when you work with it to use this theorem to slightly modify this definition. So if we have a Riesz space with weak order unit and we have a positive, okay, we have that, but we have a positive order continuous projection on E, which then gives us that there exists a weak order unit such that TE is equal to E if and only if this T maps weak order units to weak order units. And so it replacing that condition in the definition with this theorem makes it easier to just find the single weak order unit and use TE equal to E. So we now have to do our Riesz analog of a measure preserving system. So let's remember a component of a member of the positive cone of a Riesz E, let's say P, needs to satisfy that it lives in the positive cone as dominated by W, and the infimum of P and W minus P is 0. And with that, we're going to then say that this ordered quadruple ETSE is a conditional expectation preserving system, which we'll say abbreviated with CEPS, whenever E is a Dedekind complete Riesz with weak order unit, and we have T, a conditional expectation operator on E, and a weak order unit little e, such that TE is equal to E, and we have an order continuous Riesz homomorphism S on E, which satisfies the property that SE is equal to E. And the last thing, the important part to make it the analog, is we have T applied to S applied to P is equal to T applied to P whenever P is an E component in E. So this analog here, if you replace your T with just the integral, the standard expectation, and you make S tau minus 1, the pre-images, and then you take P as a set, then you're going to get the result here that the measure of the pre-image of set A is equal to the measure of A. So it gives us a good abstraction there. And so the next one, to build an F algebra, we're going to take a Dedekind complete Riesz E with a weak order unit, let's say little e, and we're going to look at this principal ideal generated by E. So we'll denote it just E, big E, subscript little e, and it's the set of all E-bounded functions which live in the Riesz E. And this gives us an F algebra structure, and we'll denote it with the dot. And using this dot, we get that P dot Q is P inf Q for all E components P and Q. And importantly, this conditional expectation, or if we have a conditional expectation, let's say T, then it will also be a conditional expectation on this EE, the E-bounded set. Okay, so the next one is not what we're proving, just what we need with that. So we're going to have our ordered quadruple ETSE, and we will say that it is ergodic whenever it is a CEPS and it satisfies this condition here. So what you should be able to see is if you replace S with tau in a measure preserving system or pre-image of tau, and you use P and Q as your sets, this will give you pre-image tau minus K of A intersect Q tends to measure of A in, times measure of B. So this does do a good job at generalizing and abstracting the ergodicity condition. And it's an order limit taken over here. So in order as n tends to infinity. Then our next one is, rather than just saying weak mixing, we're going to specifically call it conditional weak mixing. And it is very similar to the ergodicity. So we're going to take our ordered quadruple ETSE, and we'll say that our system is conditionally weak mixing when this is a CEPS and that condition is satisfied. And it's not just pulled out of air and put there. There is a way to develop it, but that's not the purpose of that. So we're just taking this as a definition for now. So once we have that, yeah, okay. This is the fun part. So, whoopsie. So, so we're going to use the Fremlin tensor product, and the notation is going to be quite important. So the O times the normal tensor product symbol is for the algebraic tensor product. And then the O times with the bar, that's going to be for the Fremlin tensor product. And then over here, there's going to be an O times with a bar, and then above it, a bar with a little delta. Okay, so we're going to take two Archimedean Riesz spaces, E and F, and their algebraic tensor product is just E tensor F. Did I change the page? I did. Okay, it's just E tensor F. And you can then have an Archimedean cone generated by E plus tensor F plus, and follow the standard construction of the Fremlin tensor product to construct this Fremlin tensor product space, E tensor bar F, which is then an Archimedean Riesz space. And it has the nice property that if E is a weak order unit of E and F is a weak order unit of F, then E tensor F is a weak order unit of the Fremlin tensor product of the spaces E and F. So now we're going to build on that, and using this Fremlin tensor product of E and F, we're going to take its Dedekind completion. So, of course, it is now a Dedekind complete Riesz space. And if we have weak order units E and F, in E and F respectively, it means then that the tensor product, E tensor F, will be a weak order unit of this Dedekind completion. And so now in a recent paper by Grobler, he showed that when we take this Dedekind completion of the Fremlin tensor product, and if we take conditional expectation operators on these two Riesz spaces, Dedekind complete Riesz spaces, that their tensor product gives us a conditional expectation operator on the Dedekind complete Riesz space. Yeah, on that one. So, in other words, when we take, if we take T, where are you? There we go. Let's take TE as a conditional expectation on the Dedekind complete Riesz space E, and let's take TF as a Dedekind complete, as a conditional expectation on the Dedekind complete Riesz space F. Then we have this map, let's say tensor delta or O times delta. Let's call it the Dedekind complete tensor map. And it happens to be order continuous. Not happens to be. It was a lot of work to prove it. It was a key part for the paper that this uses. And what it gives then is that TE, tensor or delta, Dedekind complete tensor product TF is an conditional expectation operator. So with that, so we have all the ingredients we need. We know what a CAPS is, we know what it is to be ergodic, and we know what it is to be conditionally weak mixing. And we have this tensor product, which gives us the order continuity. So we also have in the Dedekind complete space, we have conditional expectation operators, and we have weak order units. And so this result is used in developing the stuff, but it's quite a nice result. So if we take E and F as Dedekind complete Riesz spaces, each with a weak order unit, say little e in E and little f in F, then we get this result, that if P is an E component in E, and if Q is an F component in F, then their product, P tensor Q, now this is the algebraic tensor product, because that's all you need when you're working with the members of the space, is a component in this Dedekind complete Riesz space of the weak order unit E tensor F. And if we take any U as a component of the weak order unit E tensor F in this Dedekind complete Riesz space, then we can construct U like this, as being the supremum of P tensor Q, such that P tensor Q is dominated by E tensor F, where I ran out of space, so I had to write it here. P is an E component in E, and F is an F component in F. So this is going to be useful for us if we go back a lot. There we go. we're going to need to have components of our weak order unit when we deal with ergodicity and weak mixing. So that's forward, great. So the next result, also a very important result to build this, is if we take two KEPs let's go with that. So let's take two KEPs and let's say E1, T1, S1, E1 and E2, T1, S2, E2, then their product represented in this form. So this is the Dedekind completion of the Fremlin tensor product of E1 and E2. This is the Dedekind tensor product of T1 and T2, which is a conditional expectation operator on this space. This is the Dedekind tensor product of S1 and S2, which will then be an order continuous Riesz homomorphism on this space. And this is our weak order unit E1 tensor E2 on this space. And this will be invariant under that. And this weak order unit will be invariant under that. So importantly, what it means is that the tensor product of two KEPs is itself a KEPs. And so using that, we can now look at some ergodicity conditions and weak mixing conditions, and using these to finally get the result that is desired. So we're going to take our ETSE as a KEPs, and we're going to take, in this case, that T is strictly positive. And we're going to take another KEPs, E1, T1, S1, E1, as also a KEPs, I said that, with T1 strictly positive. Then what it means is, if we take this Dedekind product of the two KEPs, and it is ergodic, it implies that each of these KEPs are ergodic. And if we have that their product is conditionally weak mixing, then it means that each of these systems are conditionally weak mixing. And now for the main result with time, if we take a KEPs ETSE, where T is strictly positive, then we have these three equivalent conditions. And so this characterizes conditional weak mixing. So the first one is ETSE is itself conditionally weak mixing. Then the second statement is that this tensor product of the two spaces is ergodic for each ergodic E1, T1, S1, E1, where T1 needs to be strictly positive. And the last one is that if you take the product of this space with itself, it is ergodic. And so this is an important result, as it now shows us how we can work with ergodic systems and conditionally weak mixing systems. So we have that the conditionally weak mixing system is equivalent to the tensor product of the system with itself being ergodic. And it's a result that appears in the standard theory, which now we can put conditioning onto it. And yeah, that leaves 5 minutes for questions, so we are done. But the papers that are important, I mean, all of them, but this one is the Grobler paper, and then there is a paper by Amin up here somewhere. This paper over here. So, any questions? Okay. Okay.
It's just a technical question, but can you go to the to when you characterize weak order the next one? Can you characterize weak order units of the tensor product? More in advance. There. Okay. In the second point, when you make U as the supremum of this, shouldn't be the supremum taking over all P times Q lower than or equal than U, because this definition doesn't depend on U, and you may have more than one weak order unit, right?
Oh, yes.
Okay, that was just. Thank you.
Repeat yes for the all. Yes.
A question, please.
Actually, I have a question.
Yeah.
Actually, I have a question as Onno and Anka are here. So, you said that E and F are Riesz spaces.
Yes.
So the algebraic tensor product.
Did it complete?
No. At the beginning,
Okay, yeah.
E and F are Riesz spaces, and the tensor product is partially ordered with the cone generated by E plus tensor F plus, right?
Yes.
So why did you take the Dedekind completion of the Riesz tensor product and not directly the Dedekind completion of E algebraic tensor F? Because if I read carefully their book, they say that the Dedekind completion of such partially ordered sets must be also a Riesz space and Dedekind complete Riesz space. I am right or wrong?
Let's not take it to that.
What you have to be careful with here is the cone that you consider. So if you just take the algebraic tensor product, then the cone in there need not be an Archimedean cone. So you have to take a proper closure first, and then you can take the Dedekind completion of that partial ordered vector space immediately. So you don't have to go via the Fremlin tensor product. But to get the proper closure of the cone, so you then have to take the Fremlin tensor cone. So if you have to define the right order on the algebraic tensor product, you would actually have to take the Riesz completion of these two spaces, take the Fremlin tensor product of that, and restrict the cone to the algebraic tensor product. And then you can take the Dedekind completion, but that's a bit back and forth.
And did you think that this object will coincide?
Where these two objects will coincide? Yes, I think so. Yeah, that will be true. Yes.
Any other question?
I have worked on tensor products, but with a topology. I know that when we consider the order on the tensor products, and in the same time we consider a topology, there the problem is big. It's interesting and difficult. If we look to tensor product of Fremla or to Lotz, or I think what Bisk and Chen, I think, have two people about this. And I think I have seen some people from South Africa where they use topology. Yes, I think I have read some people from. My question: why because I think when you consider just order structure, there is not a strong difficulty to look to the problem. But when we use topology, there the problem become serious. My question: why you don't consider?
I think because you answered your question, it's quite serious. No, but no, so I haven't looked at any topology. So just with the Riesz spaces. There is some work festering in the background where I have been looking at some topology, but nothing advanced yet. That's close to doing anything serious. Anyone else? Or am I free? Oh.
How long from beginning to end of this paper? Time.
A few years. I think 3. Yeah.
And some additional authors.
Yes.
So if there are no more questions, let's thank the speaker again.